So this example comes from the 90s. It was some study, and yeah, I think that the words were, it was like some sort of sentence scrambling task or whatever, where hidden in this are, frequency of, I think they said elderly related words. So
Yeah,
like
yeah, elderly related
words,
words.
yeah, words related to aging. And so it's like, yeah, like old and Florida and retirement. And so this sort of subliminally affected, the claim is this subliminally affected their walking speed. And, you could imagine that, like why stop with elderly related words? Maybe the lengths of the words matter, or maybe, the way that a word is pronounced, like if it flows or if it's like really chopped up, that could also affect your speed. And you just think that if I can imagine, 100 of these, and they all seem to be kind of equally valid over here. And if it's the case that there are 100 that do, that are independent of each other and, affect your walking speed by 13%, then yeah, I mean, like that basically, like just like random variation among these different factors would routinely have people going, twice as fast or half as fast. So
Yeah, you could actually imagine that if two people went for a walk via sort of accessing the wrong maledictions in the process of their conversation, that effectively they might even be able to injure themselves due to the unnecessary variability of walking speed. Like, yeah,
exactly, it's dangerous. I
yeah,
mean, these
yeah, it's
effects are
dangerous.
very potential. I mean, like, yeah, if you draw them to maybe not the logical conclusion, but an extreme conclusion, then it becomes sort of like kind of apparent that it's a little maybe nonsensical.
Two
Um,
gerontologists go for a walk and become frozen in space. So, Chris, if we just say Andrew Gelman's name a whole bunch at the beginning, do you think more of the statisticians will be interested in listening for longer? Should we just try that? Andrew Gelman, Andrew Gelman, Andrew Gelman.
Andrew Gelman, I guess we'll summon him.
All right. Yes, if you look into a mirror on Halloween and say Andrew Gelman's name 3 times, he will be summoned to your location, and maybe blog about it later.
Yeah.
Cool, but yeah. So today we have a really fun episode. It's on the Piranha problem, which I think has been discussed for a number of years in statistics. But what I really like about so Chris came up with this paper on the Piranha problem, and it has a lot of the mathematical aspects of this sort of well-known scientific problem. And what I appreciated about it is that previously I only understood this from sort of a how'd you put, like, I had an intuitive view of it, but Chris went through and just knocked out all the math on a large number of sort of these important aspects. So I think we're going to start by defining the Piranha problem, and then going into essentially what your paper's off, because this is a really great example of using scientific reasoning and critical thinking directly applied to the way people make scientific statements. So Chris, welcome to the show. Yeah, to begin, what is the Piranha problem?
Yeah, so I would first like to say that, this is actually a collaboration with a few people. So while
Andrew Gelman?
Andrew Gelman is one of them, but there's a few people on the paper that, I definitely have to give credit to, that it's not just me in this paper. It's also, my wonderful co-authors that did it, that are there as well.
Yeah. This is actually all just a trick to get Aki Vatari to come on at some point. So I'm just slowly reeling him in by getting all his co-authors to come on. But yeah.
Yeah. So, but to your original question about what the Piranha problem is, it's this question or problem that occurs when you think about many sort of statistical studies in aggregate. Mm-hmm. So the question is that, suppose that you have some outcome variable that you are really interested in, that has attracted a lot of attention. For example, voting behavior would be one of these. And then you want to ask, what affects voting behavior? What out there actually, if I measured it, I could also tell you a little bit about how someone might vote. And you can imagine a whole bunch of different ways in which people could go about different variables that they can measure alongside voting behavior. And the question is, how many of these effects are likely to be there? How is it possible for us to put a bound on how many such effects can actually exist? And the reason that we think about this in terms of piranhas is because you could imagine that each one of these, effects on the outcome variable of interest is like a piranha. And if we could show that it's not possible for there to be many such effects, this is almost as if the piranhas are eating each other, that you can't have too many piranhas in a single tank. There's just not enough room. They're going to cannibalize themselves and you'll only be left with a couple of piranhas.
Cool. And so I guess, I first heard about this, probably about 4 or 5 years ago on Andrew Gelman's blog. And he was, as you said, it's with regard to social phenomena, where you have a lot of people saying, you do these small things and you can have these large effect sizes, like some perverse version of the butterfly effect, except that it's always guaranteed, things like that. So I guess part of the problem is the nature of these claims, that these, if you have something that you care about, like voting, and you have some, some confounding effect. I think he likes to bring up like whether or not your college football team is winning that year, or women like during their like menstrual cycle, and all these unusual correlations that pop up. And the nature of the claim, though, isn't that, oh, these are correlated with things that actually matter. The problem is that they're actually claiming this is predictive, and it's predictive replicably. And so in that it's predictive, the magnitude, the effect size of these things is independent of everything else, as in we've controlled for the confounding and we still find these effect sizes. Is that that's sort of the nature of the claim, right?
Yeah, that's the nature of the claim that we're trying to go after, or that we're trying to understand a little better. Is like for such claims where you say that, yes, shark attacks, the number of shark attacks is somehow predictive of voting behavior, or the performance of local college football team is in fact predictive. The question is it possible for all of these things that are seemingly independent of each other? Is it possible for all of them to actually make an impact on voting behavior?
And have a large enough effect size to be noteworthy, I guess,
Exactly.
to be worth writing home about or writing your journal. Cool. Yeah. So, I mean, that is the interest of the problem. And the reason that it really caught on with me is because effectively, a lot of the times when we make sort of like these scientific claims or claims in studies, we think that we're just making claims about what's the nature of the data and things like that. But the fact is we are actually, or that these claims aren't as serious as the claim you're making if you're bringing statistics into it. So by nature, you bring in statistics and talking about the correlation or the effect size and things like this, you're actually making very strong mathematical claims. It's one of the reasons why it's why we couch our statements in science and couch them in statistics, so you can make these strong, interesting claims. But the problem is that those claims come with the baggage of logical rigor. And so I think what's cool about these problems is like, okay, let's evaluate the rigor of these statements. Let's evaluate the mathematical implications of saying that there's 20 different ways that you can have a high effect on voting patterns.
Exactly. Yeah, that's exactly the point, is that once you've stated something along the lines of we measured, and we, like in the literature, there is, say, 20, 50 effects out there, each which we've shown are correlated with the outcome variable, and the correlation coefficient looks like 0.2 or 0.3. Now we can actually sit back and say, is this mathematically feasible? Or or what conditions actually allow this to be mathematically feasible?
Yeah, I like that, the issue of what conditions, because effectively it's not just that they're saying that there are these things with these correlations, these effect sizes, and that there's 20, 30, 50 of them. It's also stating, and they're independent. And so it's saying effectively, and we controlled, therefore these things, the magnitude of this effect should be independent, as opposed to just simply correlated. Yeah, cool. Hey folks, we're a few minutes into the show. This is usually the part where the podcaster talks about their sponsor or something. I'm not going to do that. But I will ask two things. One, if you leave a like or a dislike based on your preference, and also let me know what you think about this topic, and also what topics you like discussed on future episodes of the show. That's it. Enjoy the episode. No, this is really cool. And so I think that sort of the benefit of your work is that effectively you went and did the math stats to provide upper bounds on what some of these claims could be, which is nice because I'm more of an intuitive statistician, where when I first read about the Piranha problem, and for those listening, I'll pop a picture up on the screen just so it's a little bit easier to visualize what I'm talking about. But I sort of imagined it like a knapsack problem with where you have a covariance matrix, and you're sequentially adding one row and one row and one row to these things. So essentially, you have your first variable is y, which everything is related to. So, for example, voting patterns or health or something like that. Because obviously nutritional gains are also a thing that usually pops up. It's like if you can improve your chances of some benefit substantially, and those things get overcome. But anyway, like the idea is like imagine that you had a 2x2 covariance matrix, and y is the thing you care about, and x is the first predictor. And it's like, okay, and that's 50% correlated. Cool. All right. And it's going to be independent of everything else. Then you add the next predictor, so x2, and that's also 50% correlated with our adjust for the covariance. But yeah, I guess it'd be 0.5 as well for that if we do unit variance and zero mean. And that's also 50% correlated with y, and it's independent of x1. It's like, well, then how many of those x's could we add on before effectively you have a nonsensical covariance matrix, because effectively you're only going to be populating the diagonal and the first column and first row, and pretty shortly you're not going to have a positive semi-definite matrix. It's not going to meet the requirements of a covariance matrix. And so that was the way I was doing it. It's just like, okay, if you start filling these things up with highly correlated and they're independent, so all those zeros in the matrix too, eventually you have to decide, well, I'm going to have to, if I want to fit in more, I'm going to have to reduce the covariance. So that's one assumption. Or two, I have to start saying that some of these things are correlated, But anyway, yeah, I sort of went on. Actually, one other way that I was thinking about it, though, was essentially like if you had data along multiple dimensions, and how, if you were basically looking at the eigenvectors and how much, once you've removed one correlate, how much variability could be left in the remainder. But that's just intuition, that was just me like processing it, not really thinking about too much. What you thought about it, and you figured out some of these things, and you went through and you did, I guess you did the correlational aspect, you did what they mean for regression models, you did for entropy. What was your strategy in sort of selecting these?
Yeah, no, it's a very good question, and I will say that like you've just alluded to right here, there's no, I don't really think of it, and I think my co-authors don't really think of there being like a single Piranha theorem. Rather, we think about these as sort of like a family of such theorems that you can prove about certain types of statistical effects. So when we decided to sit down and work out some of the math over here, I think that that maybe the easiest one to think about is this correlation type thing. Like just like you're only looking at pairwise correlations. Can we somehow make some sort of statement about that? And in fact, actually, the sort of intuition that you built over here of this, looking at this covariance matrix and adding ones along the diagonal and in the first element, this is, I think, a perfectly valid way to actually prove a Piranha theorem. This is perfectly valid. The way that we did it for the correlation was a little different. It turns out that you can show one of these correlation Piranha theorems just through Cauchy-Schwarz. It's like just a really beautiful, sort of like an elegant application of Cauchy-Schwarz. And actually it turned out that, so after we sort of proved this sort of first one, did a little bit of searching in the literature, and actually found out that this was actually known before. So We found it on a Terence Tao's blog. Yeah, it was a little bit surprising to see that he was thinking about this.
Yeah, no, that's like probably one of the best lesser known blogs that's out there. I'm not sure if it's like super popular among statisticians. Since I'm more in the data science area, but no, Terence Tao's blog. If we're thinking about the same one, or he keeps multiple blogs, that is a very good resource. I'll pop that up on there. Cool.
Absolutely, yeah. And he actually called it so. So I guess apparently he found it in some source before. He actually called it van der Korpitz inequality. But I haven't yet been able to sort of track down the original over here. But yeah, I think that it's something that it's actually so whenever you prove something that seems very interesting, and at the same time it only took 3 lines, you should immediately be suspicious that other people have sort of thought of this, and in fact that is sort of the case over here. But I think that what we try to do is we try to reframe this, going from so Terence Tao had a particular reason for looking at these types of inequalities that occur in very deep areas of mathematics. Over here, we sort of saw maybe a more immediate application into how to think about sort of statistical effects in the social sciences, for example.
Yeah, I really I guess a large part of it is the framing, because when I was, even I was surprised that if I was able to intuit the basic relationship, that it would be sort of a fairly tractable proof, at least for some of these examples, like for the entropy one that we'll get into, maybe less immediately available to some of us lesser mathematicians, but at the same time, I think that the framing of the problem is, at least that's what fascinates me the most, because effectively there's a language translation of this mathematics. There's a logical translation that very much affects how we make statements. And even for things like, if you're in machine learning, the idea of, how many additional features could you add that maintain their independence before essentially they're going to start cannibalizing each other. And also the nature of the cannibalization, how many times can you have how many positively correlated variables can you add before you need to start finding a negative correlation, and essentially something to sort of reset the variability back. But yeah, maybe to go from here, how would you like to proceed? Should we just restart? I feel like I've been babbling enough that maybe we should just restart with the piranha problem. The idea is
Okay.
The idea is if you have a small pond or a fish tank, you can only put so many piranhas in before they start eating each other. Before essentially you run out of space, and so effectively you're going to only have a small number of piranhas. And the piranha requires them essentially to be independent. They don't play together, I guess. And for these claims, essentially you're saying for any entity with variability, if you have a certain number of covariates, correlations, and things like that, that those won't actually. You can only have so many of them that are 1, independent, 2, very important. Actually, that's it, isn't it? Yeah, both independent and very important.
Yeah, exactly. So basically, these piranha problems, in a bunch of different ways, they assert essentially the same thing, where there are 2 possible worlds that you live in. One of them is the one where all of the claimed effects are real. Like you actually do have, large effects, and everybody that's measured these things, they didn't screw up with the data. It's not measurement error. It's really there. But in that world, you also must have that they themselves are cross-correlated with each other. So there are, they, for example, cannot be independent. That's a consequence. So you're either in that world, or you're in the world where all these effects are independent of each other. All these covariates that you're thinking about are independent of each other, but then that means that only some of these measured, claims can actually be true.
Mm-hmm. True and strong. But yeah. So sorry, I'm excited about this topic, so I keep interjecting uselessly. But yeah, no, it is cool. Again, playing with that. So I had some quotes from your paper that I thought would be useful for us to talk through. And this will also lead some places. So one of them is from page 2 for anyone who grabs the paper, and the paper will be linked in the video description. Some of the claimed effects are smaller than claimed, or some of the claimed effects are smaller than claimed, or some of the explanatory variables are essentially measuring the same phenomena. I think that's what you just described. And part of this is, is that some of this just sharing the random noise or measurement error. Because part of what we can think is if the effect size is very large, it also might mean that there's just a lot of noise in measurement. So the fact is, in order to have a large effect size, essentially you are just capturing just a very noisy process.
Right. Yeah. So it could be, so if there's a large effect size, then you would hope that it's sort of like the signal to noise ratio. That's maybe one sort of like way to think about this. If that's large enough that it sort of stands out above the signal and you can reliably pick it up, right? I mean, you would hope that's the case, but yeah, the point over here is that that basically you can't have enough of these variables that are independent of each other and are also above that noise, like that have like a strong enough signal to noise ratio.
Mm-hmm.
So yeah, I mean, like, so, like if you want to ask the question, so how is it that looking back at, these studies showing that shark attacks, college football games, hormones, all of these things have an effect on voting behavior. How is it the case that all of them seem to be independent, and they also claimed a large effect size? What we could say is that, well, it's probably like for some of them they must have picked up this sort of like too much noise in their measurements, and it's not actually it's not real at the population level.
Yeah. And I guess one other bit that I was thinking about is that, for example, with regards to voting, is there even that much evidence that there's variability in voting? I thought that basically people pretty much, it's about like what? There's maybe about like 11% of people are undecided going into any given election, which means it's a very small range from which to have variability. And then to have these things which can have large effects on the variability, if you're saying 20% more likely to vote for Barack Obama or something like that, 20% is a very big effect that you can have for something that has very low intrinsic variability to it, because people set in their ways. And so to me, that seems like, I sort of think about it as sort of like the law of total covariance, where I fear that if you essentially line these things up enough, that you would effectively be getting enough added variability that exceeds the variability of the actual variable of interest, if you believe that they're independent.
Right, exactly. I mean, like that's the other way to reason about these types of Piranha theorems is that they are in effect finding what is the possible cap that you could have, of these sort of independent, variables. So.
Yeah, and I think you gave a really great example in yours, where you're talking about walking speed. And so effectively, just to recap, there was a study that showed people or told people sort of like geriatric or debilitating words, just sort of downer words like old, infirmed, fall, I don't know, things like that. And then they, I believe you said, surreptitiously recorded them as they left the study area, and they measured their walking speed, and they found out that the people who are shown these sort of infirming words, these curses, if you will, slowed them down by 13%. And your example was that if you had X many of these type of effects, you could essentially be doubling or halving the walking speed of participants without them even noticing. And it would be a relatively small number, right?
Right. Yeah. So that's sort of exactly the point, like, which is that, so this example comes from the 90s. It was some study, and yeah, I think that the words were, it was like some sort of sentence scrambling task or whatever, where hidden in this are, frequency of, I think they said elderly related words. So
elderly related words.
Yeah, words related to aging. And so it's like, yeah, like old and Florida and retirement. And so this sort of subliminally affected, the claim is this subliminally affected their walking speed. And, you could imagine that, like why stop with elderly related words. Maybe the lengths of the words matter, or maybe, the way that a word is pronounced, like if it flows or if it's like really chopped up, that could also affect your speed. And you just think that if I can imagine 100 of these, and they all seem to be kind of equally valid over here. And if it's the case that there are 100 that do that are independent of each other and affect your walking speed by 13%, then yeah, I mean, like that basically, like just like random variation among these different factors would routinely have people going twice as fast or half as fast. So
Yeah, you could actually imagine that if two people went for a walk via sort of accessing the wrong maledictions in the process of their conversation, that effectively they might even be able to injure themselves due to the unnecessary variability of walking speed. Like, yeah.
exactly, it's dangerous.
Yeah, it's dangerous.
Potential. I mean, like, yeah, if you draw them to maybe not the logical conclusion, but an extreme conclusion, then it becomes sort of like kind of apparent that it's a little maybe nonsensical.
Two gerontologists go for a walk and become frozen in space, something like that. But yeah, cool. Another quote from page 2 that I thought would, I was a little bit wondering about this. Is it says, at first glance, it may be somewhat surprising that one can rule out the possibility of many independent variables having large effects on a single outcome. Indeed, there's nothing functionally or causally that excludes such dependencies. I was wondering a little bit about this. I know it's like a very specific bit, but I was wondering about talking about the functional or causal that excludes having these types of dependencies. What are your thoughts on sort of the relationship that these things have with sort of functional descriptions, causal descriptions, and how we can use those aspects to reason through? Shark attacks aren't taking down too many voters, state of the economy might, but you get that idea. What is the interplay between the causal and functional understandings, and how would that have saved us from these mistakes?
Right. Yeah. So I think that what the quote is, I think what that part of the paper is really trying to communicate is that, this that on one hand, when you think about these effects, it's like you can say, okay, yeah, of course, like I can come up with these correlation matrices and show that eventually you'll get something that's not positive semi-definite, and therefore correlations can't be this way. But if you sit down and think, you can come up with ways in which you can have, I mean, there are ways in which you can have many different variables that do have a functional relationship with some outcome.
Mm-hmm.
So there's somewhat contrived examples, but I think about them in terms of like the type of relationship I'm thinking about is some sort of multiple light switch problem. So think about like you have a bunch of light switches in your house that all turn on the same light bulb. And what the property that these have is that if I, for any fixed position of these light switches, if I flip one of them, it will change the state of the light bulb, right? Like it'll flip it on or it'll flip it off, So when I think about the light switches as explanatory variables, each of them does have a functional relationship with the light bulb. But the point where the Piranha problem comes up is if your observations of light switches and light bulbs were purely observational, like you only observed them and the light switch positions were independent of each other, then it turns out that you would actually, like statistically, not be able to measure any relationship between the light bulbs and the light switch. Like for this particular example, if the light switches are independent of each other, then their correlation with the light bulb is zero. If you plugged it into a regression, they would also, all the variables would come out zero. You wouldn't be able to statistically detect this. So yeah, so I know that this has been a very long answer to your question, but the point that I'm trying to say is basically that there's a difference between what we think about as a functional relationship and what we can sort of determine statistically, and sort of like these are like some of our intuitions about functional relationships can actually be, I think, a little misleading statistically.
Yeah, definitely. Actually, this is one of the main points that I thought, like, oh, I really appreciate that someone thought this through. It's this sort of light switching example because just for those who haven't done their like math stats in a while, you can have variables. You can have uh, variables that are, independence and correlation are not, it's not uh, if and only if. So let's think of this. You could essentially have X determine Y deterministically and have zero correlation with Y via, for example, these light switching examples. And they seem like, sort of perverse examples, but the fact is, in reality, these things can pop up. And one of the things I thought was really cool about the mathematics is I was wondering, it's like, oh man, did he account for all these? Like for all these sort of like weird little brain teaser examples, but I guess the math works out, so it did.
That's what happens, I guess.
Yeah.
That's a nice
That's
thing
one
about
of
a
those.
proof, right?
Yeah. Yeah, no, that is cool. So just for those who are interested in reading the paper, Chris, you had four examples, and I think we'll probably go through like three of them. And so you proved this in three different ways or three different applications. One was for correlations, so the Piranha problem applied to correlations. Another was applied to linear regression. And so both of those first two are linear. And then you also have one on mutual information. So it's saying, okay, now let's not assume these linear relationships. And well, I don't think we need to go through the math. I am curious about the strategy because I think that gets at the intuition of these problems a bit better.
Yeah, it's okay. So, right. So what is the strategy for proving these different types of things? And I think I guess I can talk a little bit about my intuition behind each of them.
Mhm.
So for the correlation one, the intuition here. So like I said, we proved this using an application of Cauchy-Schwarz. And when you think about Cauchy-Schwarz, actually, it doesn't. I mean, like your first thought is probably not in probability. Your first thought is probably in vector spaces and linear algebra. And it turns out that there's obviously a kind of a beautiful relationship between vector spaces and probability spaces. But when you view these sort of like random variables in terms of their vector, like the associated vectors, and you think about inner products, and when you're thinking about the covariances, quickly what you begin to realize is that there's not so many ways that you can have two vectors pointing in the same direction as a third vector, but also orthogonal to each other, right? So
Yeah.
orthogonality, which is the same as sort of like independence, or zero covariance, is sort of the constraint that we're putting on things, and that's sort of like was the intuition behind that sort of proof.
Yeah, I like that. So, for example, for very early career statisticians and data scientists, you might remember, for example, back when you're learning about PCA, and effectively what you're trying to do is find the vectors that maximize variance. And so the idea here is that as you're drawing these things through, these actually have strong relationships. Well, they're pretty much determined by the covariance matrix. I don't think you can calculate one without calculating the other. But the idea is if you continually add more and more vectors, how many of these things can you actually add while still keeping them all orthogonal to each other? As you add more and more dimensions. At least that was the way that I was thinking about it. And eventually, what would be left of your outcome variable would be infinitesimal, because you couldn't add any more orthogonal ones that still maintain their orthogonality to the rest of the variables that you had already added.
Exactly. Yeah. So what you can think about is that each time that I throw an explanatory variable in my outcome variable, I'm basically I project away that direction, and then I'm left with and then the outcome variable in after this projection has to be shrinking,
Mm-hmm.
right? And the amount that it shrinks is directly related to the amount of correlation that there was between them.
Until eventually, what is left of the projection essentially becomes presumably a vector with zero magnitude. Would that be it?
Exactly, or magnitude below
The threshold.
whatever the threshold is that
Yeah.
you want to claim that there was an effect.
Yeah, and I guess that's one bit that a lot of your proofs are saying, assuming that all of these correlation coefficients are greater than a certain amount. So effectively, you're assuming a magnitude greater than or equal to a certain amount. Is that
Yeah,
all right?
exactly.
Cool.
Exactly. Yeah. So, I mean, like, I think that they're phrased generally in a way that, like you could, um, have them for arbitrary, sort of values. But
Hmm.
the easiest way to think about it, to conceptualize, is say, okay, imagine that they're all at least some threshold.
Hmm.
And that threshold is what we might call a large effect.
Yeah, and actually, I was thinking that one of the ways this could be is effectively, let's just say all the cool stuff's already taken out, and now you're just basically the person who wants to quibble over the small details. One thing that you could do is you could have the remaining variance of the outcome of interest, and essentially you could then create a new, I guess it would be the new tau bound on the remaining one. So effectively, say you had a few large effects that you aren't going to try to do, you could then alternatively just look at what variable remains once those large correlations are taken out, and then you have a new bound that you apply to these smaller ones that you're still trying to figure out and bound.
Exactly. Yeah, that's definitely one way that you can think about it.
Cool. I feel like I've just sort of like butchered your really nice proof with just a lot of like heuristics and hand waving, but it is really cool. Now for the oh, actually one other question was, we talked about the correlation being the magnitudes of these correlations being greater than or equal to a certain amount. Um, Positive correlation versus negative correlation. Is there any aspect in there that sort of confounds or makes this difficult?
No, it turns out that that's not a problem, because what we can do is we can just, um, so for any variable that has a large negative correlation, you can just imagine taking the reverse of it, and
Yeah.
now it has a large positive correlation. And now we can flip all of the variables that were negatively correlated. We can flip them to be positively correlated with the outcome,
Hmm.
and give a bound on that. And that's the same as giving a bound on sort of the magnitudes of the correlations.
Cool. Yeah, no, I appreciate that. Now, so the next one, the linear regression example. What was your so first? Maybe we'll start with what statement do you make with linear regression in the Piranha problem?
Right. So the theorem goes, so it's okay, so it's a little bit hairy. So let's just think about the first case is, imagine that you have your covariates are independent of each other. Okay. And also in all of these Piranha theorems, you should also think about your um, random variables as being standardized. So they have, mean 0 and variance 1. Okay. So imagine that you have these, covariates that are all independent of each other, or at least, uncorrelated with each other. Then if you plug those into a regression, uh, a linear regression where you're regressing on your outcome variable y, and you looked at the resulting coefficients, then the sum of squares of those coefficients. So if I sum up those, usually we use in statistics, we use beta. So if you sum up those beta j's associated with each of the covariates, and you square each of those, that is bounded above by 1. So what that means is basically that the number of coefficients that can be larger than, for example, some value tau, is less than like 1 over tau squared. So the number of coefficients that can be larger than zero point 0.1, that's less than 100.
Hmm.
That's less than 100.
Yeah. And so I guess one thing is that it's not obviously like an additive. It's not like a perfectly additive relationship. It reflects on essentially the square of a lot of these values.
Exactly. Exactly. Um, And so, okay, so if your variables aren't perfectly correlated, or aren't perfectly uncorrelated with each other, if they, for example, have um, some correlation with each other, then this bound gets blown up slightly larger. It depends on the minimum eigenvalue of this correlation
Hmm.
matrix. So it looks like, instead of like the sum of squares being bounded above by 1, it's bounded above by 1 divided by this minimum eigenvalue. Um, and that's the proof is kind of actually, it's one of those things where it's actually, the proof is kind of like in the intuition. So the idea is that if I take my covariance matrix and I invert it, and I multiply it by my variables, this is a process called whitening. It's something that we do in data analysis all the time. We take variables and we whiten them, and what that whitening does is it makes them orthogonal to each other. Okay, so you took your original variables, which were maybe correlated with each other, and then we applied this, and now we get them uncorrelated. And now we can look at the regression coefficients on that, and that sort of like tells you sort of this relationship over here.
Hey everyone, we're in the final stretch of our episode. And before you go, I'd really appreciate if you could give me feedback on 3 things. First, what was your favorite question of the episode? What did I do right? Secondly, what question did you wish that I asked but didn't? And third, what questions were brought up by this conversation that you'd like answered in the future? That's it. Enjoy the rest of the episode. Yeah, cool. That is good. And as you said, I like when you said the proof is in the intuition, because I'm pure intuition. So if it goes beyond intuition, that's all I got. But yeah, that is a cool one. Now, so those are 2 of the linear examples. And again, I think one of the reasons that those are good is those really speak to the problems about the social scientific reporting, just these general sort of spurious results, inferring the butterfly effect where there isn't one. Those 2, I think, really hit on that initial motivation. The mutual information one, I think, is just, that's just, it's icing on the cake. It's the cherry on top of the sundae a bit. What was the motivation behind that? Was it to essentially make it more applicable to some of these like predictive methods, or what were you thinking?
Yeah, I mean, I think so. So, after we proved a couple of these Piranha theorems, I think we sort of like you start to see them everywhere, right? You start to see the piranhas everywhere. And in this one, like I come from a machine learning background, and obviously, we don't, in machine learning, we don't assume that all relationships are linear. As well as many other fields don't assume linear
Pretty much most interesting relationships are nonlinear and
Exactly.
complex. Yeah.
Exactly. And so, I mean, like the natural thing still holds with, like how much predictive power can sort of like be added, by like if I have some, variables and I look at their individual predictive power, how many such independent variables can you have? It didn't seem like it should be possible for there to be many. Like it seemed like there should be some type of Piranha theorem here. And this mutual information thing is kind of another way of getting at that.
Yeah. Was there anything specific that you wanted to highlight in sort of the intuition behind that, or
Yeah. So okay. What we end up showing over here is that if you look at all the mutual, like if I look at every variable covariate xi, and I look at its impact on my outcome variable, then the sum of such mutual informations should be bounded above by some term that depends on the mutual information among the xi's, and plus this term that depends on the entropy of y. And the intuition over here is that, like, okay, so if your random variables are independent of each other, then that term that depends on the cross mutual information is just 0. So you just have the mutual informations between your covariates and your outcome variable. That sum is bounded above by the entropy of the outcome variable. And basically, what you can think about is you can think that each of these independent covariates is trying to pack some information into y. But there's only so much information you can do for when you have bounded entropy. So like the entropy is, you think about as a bound on the information. And over here, this is explicitly telling you, how many large, aspects of y can I explain individually.
Yeah, I like that a lot. And so I guess when it comes to this sort of packing, if you will, I think one of the things that comes back is, and correct me if I'm wrong, that a lot of these things, a lot of these bounds these bounds definitionally, they're only here because essentially scientists or researchers are insisting on saying that these variables are all independent, that they essentially have no cross information, or that they things like that. So which is important because of course we do want to be extracting the independent effect from correlational effects. But again, a lot of these things, it reminds me of the big math tome that Lakatos wrote, where effectively he's sorry all this. He basically talked about mathematics and how you build up assumptions and build up requirements in mathematical proofs by essentially taking something simple and then saying, well, I want to say more and I want to say more. So it's like if you want to say something simple, you don't need very many assumptions. If you want to say more about it, you need to have this assumption laden area. And I think that effectively where science has moved, we started making these assumption laden claims, but we forgot what all the assumptions were. Saying these things like we've controlled for this and these things are independent. And I really like how you've just come back and saying, well, like here are the logical mathematical implications of these claims, just FYI in case anyone forgot. And if we reapply these, we can see that some of these claims do not essentially hold mathematical or scientific water. Yeah.
Yeah, that's exactly right. I think that's essentially that's one way to view this paper, is that what we're trying to do is basically just give some type of perspective, right, on kind of a field as a whole.
Cool. Again, another quote, because I thought this was interesting and it would lead to an interesting question. But on page 8, for anyone who's reading, you have this quote that says, "We cannot directly apply these Piranha theorems to data." And could you explain that? Because the idea is, if you're thinking about, expected value and variance and things like that, we can plug and chug. We can play with these things a bit. You can add dimensions to a covariance matrix until it pops. I'll read it in full so that people who are just listening can read it. But the quote is, although we cannot directly apply these Piranha theorems to data, we see them as providing some relevance to social science reasoning. The motivation of this review article is to collect several interesting results regarding the distributions of correlations or coefficients, with the aim of fostering further work on mathematical and statistical models for environments with a multiplicity of effects. So, obviously the people who've been listening to the podcast, the reasoning around, or, the aspects of scientific reasoning around these statements is a very interesting. And this also brings up the issue of multiplicity, multiplicity, which we've been discussing. But when you made the statement, we cannot directly apply these Piranha theorems to data. I guess in some ways you could, but what were you sort of trying to highlight when you say that we can't be applying these theorems directly to data?
Yeah, you're absolutely right. Like certainly, what you could do is you could scour the literature and you could look for for example, on voting behavior, every study that claimed to have measured some type of effect or correlation, look at what those numbers are and simply, try to run the Piranha machinery to tell you like, okay, we can conclude that some of these must be false or at least dependent of each other. So that's, you could do that. I think one of the things that we're lacking though in this paper right now is the ability to sort of tell you any sort of actionable information over here. So we can't tell, we can tell you, yes, maybe there's something wrong, but we can't tell you what's wrong. And we can't tell you like exactly, which of these studies is most suspect or anything like that. So while this is like, I think a paper about, reasoning about, like a body of work, it doesn't really give much in terms of, practical applications. Like there's no crank that you can turn to fix this, for example.
Yeah, I mean, it's like the idea you can't be taking this and applying it to the prosecution of a paper, or say, here's our evidence against some found thing.
Exactly. Like we can't say, yes, this paper on shark attacks is the culprit. It's the reason why everything breaks. And if we just remove this from the literature, then everything is okay. Like you can't, we don't give any sort of mechanism for doing that.
Right. It would be essentially, just to reiterate, that you are having to take these things in aggregate. So the idea is like, for example, the walking paper, that you'd find multiple walking papers enough that, I think you have a quote where it's like with 100 studies, your 13% effect size can make people twice as fast or twice as slow without them noticing. So it's reviewing these things in aggregate, dependent on the claim that people are making, which is that they have found an independent effect.
Exactly. Um, or like conversely, if they don't make any sort of claim of whether or not it's independent of things in the literature, it does at the same point, I think, highlight that it could not be independent.
Yeah. And I guess it brings into one question, because this is good a place to talk about it, is when essentially, let's just say someone comes into enters the literature and says, I've now found an effect size, like some correlation of like 0.25 or 0.3 or 0.4, something like that. Just big, just comes in like a big old SUV into a parking lot and just pushes other little cars out of the way. Actually, that is the analogy. The question is, what cars are you going to push out of the way in order to accommodate an effect of this size? Because effectively, you're saying this is independent. If these other effects are taken up and they've been accepted, then you have to be saying that these other effects need to accommodate you, given that you're saying that they're independent. And so should the researcher come in and say, we are coming in, we found this effect size, it's statistically significant, our design is sufficient to have actually found independence, and now we're calling BS, unlike these other articles, or like these other articles in aggregate must be wrong. But no one obviously wants to say that, because obviously the rest of the research community would sharpen the knives at you.
Yeah, I think that it's a really hard question. Like once you sort of like see the Piranha theorem, then you realize that we're faced with some type of dilemma, where on the one hand we could sit down and say, okay, no new effects unless you measure yourself against every established effect and show that you are sufficiently explaining something that's not already in the literature. But that seems so like draconian and difficult to implement, and just like expensive. And so it's like, but on the other hand, if you do nothing, then you're sort of left with this kind of Wild West thing where we say, sure, yeah, everything is a potential effect.
Everything is awesome, yeah.
Exactly. And so I think it's and that's, I think, one way in which I think that we wish that we could do more in terms of adding sort of like machinery, some type of machinery. This is, I think, a really great question of like what can be done about this. Like what kinds of statistical practices could we encourage for everybody to do, so that it's not too onerous on any individual researcher to actually discover something new and truly independent.
Cool. Yeah. One thing that caught my interest in this is you make numerous references to Brownian motion in your work, and there's a lot of Brownian analogies. Are those like briefly worth going into, or should we just leave that be?
I mean, we could just, I guess I'll just, say, I think, the analogy over here is that, okay, so Brownian motion, is, it's a mathematical description of what happens to, molecules in a gas or a liquid, as they are sort of bounced around by their neighbors, right? And so you think about a molecule over here, and then it gets hit and it bounces this way, and then it gets hit by another molecule, and its motion is random, and it's somehow being affected by a whole bunch of things. And I think that like the kind of analogy over here is that somehow like none of these effects could be like, you couldn't have a whole bunch of really consistent large molecules that are always bouncing into it, because otherwise the position of the molecule would be going in crazy positions. Like everything has to be kind of small in order to sort of like obey sort of the physical limitations of the system.
Cool. Yeah, no, I like that analogy. I very much enjoy when people can construct analogies that are very easy to grasp. On the issue of, we're just going to start ticking off some of the cool stuff, because obviously there's a whole bunch in this paper. I'd strongly encourage people to read it. There's a lot of dense stuff. Like when I read this, I was pretty much excited for the entire weekend afterwards, just thinking about things, getting doodling down on some math, doing some numerical simulations and things like that, trying to test these bounds. But you talk about the implications on this for regularization, and how you might have like sparsity in Bayesian priors. And what you discuss in here is that when you have a place where there's going to be a small number of large effects and I guess an infinite number of small effects. That creates priors where you'd effectively see a spike right at 0. So effectively the spike is where there's a high density of things with basically no effect. And then there's going to be, I guess, this very long tail populated by a small number of examples, and how you might apply that to Bayesian priors. What are your thoughts about that? Because obviously you mentioned things like uninformative priors, sparse and correlated priors. What is the interplay between these things? Because obviously I thought if you're going to have a big spike and a long tail, that isn't really going to be an uninformative prior, except maybe in the extreme tail or something like that. But what's your call?
Yeah, so I think, so the interplay of sort of like these types of, prior distributions or different ways of doing regularization, that the interplay between those and Piranha and sort of like these Piranha theorems is that the Piranha theorem says that it says, okay, you can't have a whole bunch of independent large effects, but there's a bunch of ways in which these effects could actually be distributed. So maybe they're all very small, or they're all like, like there's a bunch of effects, but they're all small. Maybe some of them are very large, but that constrains everything else to being 0. And all these different ways that you could imagine, like what we've noticed is in the literature, like all the ways in which you could imagine sort of the constraints of the Piranha theorem being satisfied, of like small, like everything is small except for a few large ones, or everything is sort of like kind of like relatively the same magnitude. These correspond to different priors that people have come up with in the literature, right? So there's like these spike and slab models, right? Where it's like, like a big spike at 0, and then everything is like, like almost uniform going off out to 0, like out to infinity. Or, like other, sort of like only weakly, informative priors or weakly sparse priors where they're basically normally distributed around 0 with some type of, variance that depends on, the errors in the model, the errors of the observed model. And, those priors actually correspond to like one of these worlds in which the Piranha theorems live in.
Cool. If you don't mind me asking a bit, with these priors, are these types of priors actually, is it useful and easy? I'll leave out the useful bit because I think I have already decided on that. But is it easy to come up with essentially legitimate probability densities when creating these priors? Because a lot of the problems with in the machine learning field, when we have these uninformative priors, they actually aren't they aren't proper priors, they aren't actual distributions. They're effectively regularizers poking at your posterior. And so to me it seems like when you're talking about are these legitimate priors, or are these mainly being used as regularizers, and we simply want to fashion them in a Bayesian framework?
It's a great question. You'd probably have to ask someone with a little bit more Bayesian knowledge than myself about the particular way about prior specification.
Wait, you're saying that prior specification isn't just like super easy? Just there's like one rule that you follow and it's all downhill from there?
No, it turns out that there's a lot of people that have spent a lot of time.
There's one or more rules on yeah, cool. Yeah, that is. Yeah, that is helpful, and I guess I won't pester you on that too much, but it is. You could definitely see how people would be able to. One of the nice things about this construction that you've made is it has given people a way to reason as they construct these things, and so you could imagine them definitely saying, "Okay, we're going to take a world where we'll entirely represent this as a probabilistic distribution," especially because the prior is essentially coming down from on high of your mathematical statistical knowledge. And I could also imagine people just saying like, I can regularize this inspired by these methods. That is.
Yeah, and I think the other sort of benefit, sort of like, okay, so maybe this is one way in which sort of Piranha theorems can inform our ideas behind Bayesian methodology. But sort of like on the flip side, we could also imagine looking at sort of specific prior models that people have come up with and asking what are the sort of resulting things that you would see in these Piranha sort of type theorems, and what sort of like effects would you expect to see in data, given that your prior effects were generated by such models. So I think that there's a lot of potential interplay here, between Piranha theorems and sort of like statistical methodology, in particular Bayesian methodology.
Yeah, that's interesting. Actually, the elicitation in the other direction wasn't something I was thinking about. So I think I'm glad you brought that up. One other question, I guess, because obviously we got to go soon, but there's the butterfly effect in complex systems. And I thought it'd be fun to talk about how these differ from the claims of these sort of like sociological, and social scientific studies. So essentially, it's the butterfly effect says, a butterfly can have a big effect. The problem with the scientific claims is that they say these things will, because like we've published it and we've checked for the independence. So these are different in the nature of the claims, but they both have the same sort of tabloid value to them. What are your thoughts on this as far as essentially the implications?
Yeah, no, so that's a great question, right? And it sort of like exactly gets to what you said, which is that like, when on the butterfly effect, like with these sort of chaotic systems, that there is a potential for a small change to create a big, destabilizing event that changes the whole dynamics of the system. That's, like a possibility, that arises in this chaos theory. But on the other hand, like you might say, like one conclusion that you might say is like, okay, you only need a small perturbation to change the system. So, let's just find how we have to tip the scales in order to change the system. Let's find the butterflies. And so like the point, and so that type of reasoning inspired by the butterflies may explain why, in the social sciences, we have seen a large pursuit, like we've seen a large pursuit of different types of, things that seem like totally, like the relationship doesn't really seem clear. Shark attacks and voting behavior, college football teams and voting behavior, like we don't see it. Like it shouldn't be clear, but the butterfly effect, taken at face value and with not really a large regard for the nuances of it, suggests that, oh, well, butterflies are just waiting to be found. You just find these little things and you can tip the scales. And maybe you can, and then, the belief is like, maybe we can actually tip those scales reliably. Mm-hmm. And so I guess the Piranha theorem is sort of like coming in and it's saying, well, no, you can't do that. Not with a bunch of things that are seemingly irrelevant. You can't reliably tip the scale,
Yeah, so it's like the idea is like, sure, maybe there are butterflies that can cause hurricanes on the other side of the world, but the fact is, if such butterflies exist, there can only be a few of them. Like you can't have the world populated with these hurricane-causing butterflies, because otherwise our world would be covered in hurricanes.
Exactly. Like I can't just go and say, okay, this rainforest is where if the butterfly flaps its wings, that'll create it. And so I'm just going to like, I really, want to study hurricanes, or I'm really,
we need data.
Like, exactly. I want the data. So I just release butterflies there and I will cause hurricanes. That isn't really how, chaos theory predicts things. And it's obviously not something that actually, occurs in statistics either.
Yeah, there's a big difference between saying this can do this and thou shalt have this effect.
Exactly.
Which I think is why we like science, because effectively it's saying we've done enough of our homework, checked the confounding enough to know that effectively there is going to be a much more mechanistic understanding. Actually, it reminds me a little bit about the comments you're making earlier about essentially having these things where you can have dependency without correlation. So effectively, the real sneaky butterflies would be the ones who can cause these things, but there's no correlation left at the end.
Exactly. Yeah. So maybe there is a particular, configuration of butterflies, but you'll never be able to statistically detect it.
Well, that is great. Once again, I honestly thanks so much for you and your co-authors for going through this paper, because, it's a very interesting topic. read, if for people who are interested, there are multiple blog posts on it. Apparently Terrence Howe has some stuff on it as well. And check out this paper. It'll be in the description. But I really appreciate you just going through and providing mathematical formality to it for people like me who would never bother to do that.
Well, thanks for having me. It's always great to discuss this work, and yeah, I mean, like if anybody wants to, like I'm always open to hearing from people about their thoughts on this stuff, and if they have ideas on this. This is, I think, a really interesting area, and I'm just glad to be able to talk about it.
Yeah, if you don't mind, how does this relate to the broader aspects of your work?
That's a good question. So maybe so this is it's a bit of a one-off project in the sense that I don't have like a large body of work that builds around this. But I think the reasoning behind it has influenced a little bit of my thinking on some recent work that I've done on machine learning. I mean, I'm not sure if you want to hear about that right now.
Oh yeah, absolutely. I was actually going to make the joke that you mentioned neural nets in there. It's like, the paper's relevant. It says neural nets in there. But yeah, no. I think that this is definitely interesting because effectively, when you're thinking about things like recommender systems, for example, where if you're trying to look at how much where to add new information, this I think is very informative because essentially it's setting bounds on what you can expect, and if you add something like that to the cost. That was just what popped into my head originally. But what are you working on, and how does this apply?
Right. So there's a really hot area in machine learning right now called contrastive learning. That's related to this idea of self-supervised learning. And it's a really cool idea where basically you want to learn representations from unlabeled data using neural networks. And the way that you do it is you take, for example, for image data, the way that you do it is I take an image and then I randomly crop it. And then I take another image and I randomly crop it. And I ask the question, I ask a neural net to be able to distinguish between whether or not these two random croppings came from the same image. And essentially, in the process of doing this, you learn a representation. And so I wanted to analyze this sort of theoretically with some great co-authors, and basically something came out that was very Piranha-like, which is that like when are these representations useful? Well, it turns out that that we can prove that they're useful when it's the case that these random transformations of the images still preserve some sort of information about this downstream task. And as it turns out, there's only so like if they preserve information about, like if they are somehow informative about each other, like if they're informative about each other, like doing these random croppings, then they must be informative of the downstream task. So it's a bit Piranha-like that there's only like so many ways in which you can sort of like pack this information before they actually, the way in which they explain each other is also explaining sort of like the label of the image, for example.
That is very cool. I can definitely see where you're going there. Yeah, a little bit what I was thinking about is just like the idea is like, well, depending on how you crop, there's only so many big crops that you can have before there's nothing left. But I think yours is a bit more sophisticated than that. But yeah, that is cool. Oh, was there anything else that you want to talk about as far as what your research is, or any other general epiphanies? I mean, you've written a smart paper. I'm just generally curious about ideas, epiphanies, anything like that.
I mean, like I think that these are at least two. I mean, like two interesting ideas that I've thought about recently. It's maybe a little out of scope to talk about a whole bunch of other things.
Yeah, that's fair. All right. Well, Chris, again, thank you so much for writing this paper. I think it was really useful and extremely interesting. For those who are worried about sort of the more mathematical papers, I think that this paper is worth the trouble, and you can appreciate it even if you basically just gloss over the theorems. I think like it has such a rich description in it. It's very useful. So, Chris, thank you so much for the contribution, both to the field and to my own curiosity on this. I really appreciate it.
Thank you for having me.